Welcome, Mode T Solutions. What I'm going to show you today is a demonstration of a proprietary reasoning architecture I have developed. This architecture reads the properties of a problem before attempting to solve it. In doing so, it provides hallucination-free outputs and significant efficiency gains. Let me show you what this looks like in practice. What you're looking at is a benchmark harness. It runs the same problem through two modes: Standard, which is a conventional solve, and Mode T, which applies the architecture, then measures the difference. The measurement is called Total Effort Score, or TES. It counts every check, every branch, every evaluation, and every backtrack. The ratio between them is the efficiency multiplier factor, how many times more work the standard approach did to reach the same answer. We'll start simple and escalate. This is a creative writing task. Write a 15-paragraph story about a battle between good and evil. Both modes receive the same prompt. Standard mode explores multiple thematic directions, evaluates each, abandons the weakest, then commits and writes. Mode T makes structural commitments immediately and executes in a single pass. This architecture didn't come from computer science. It came from 20 years of diagnosing failures in mechanical systems, aircraft, engines, industrial processes. Every stable system I worked on resolved through the same structural relationship. That relationship turns out to be universal. This proprietary architecture uses the properties of the problem to determine the requirements for the solution. Applied to computation, it eliminates work that was never going to contribute to the answer. The architecture is patent pending. Every AI company on Earth is facing the same problems. Inference costs are exploding as models get larger. The scaling wall means each generation demands exponentially more energy and compute. And hallucinations, outputs that sound confident but are factually wrong, mean the results can't be trusted in any domain where accuracy matters. These aren't separate problems. They're the same problem. The system is doing too much unproductive work. It explores when it should commit. It guesses when it doesn't have enough information to answer. It burns compute on paths that were never going to lead anywhere. This architecture addresses all three. It reduces inference cost by eliminating unproductive computation before it happens. It extends the scaling boundary by making existing hardware solve larger problems. And it eliminates hallucinations by identifying when the information needed to answer doesn't exist, and stopping instead of fabricating. The standard approach scored 14 total effort steps. Mode T scored only 9. That's a 1.6 times efficiency gain. Both outputs are complete, coherent stories. On a generative task, the gains are moderate, around 1.5 times to 3 times, because creative work doesn't have much wasted computation to begin with. But watch what happens as the problems get harder. Next, we will move on to a bin packing problem, where the standard mode wastes computation to derive the optimal solution. Every problem, regardless of domain, has properties that define where the answer can and cannot exist. This architecture identifies those properties before any computation begins. What it finds determines how much work actually needs to happen. In most cases, the answer is far less than what current systems are doing. So how does it work at a high level? Current systems receive a destination and search for the map. This architecture receives the destination and already knows the map. It doesn't search faster. It never searches where the answer can't exist. That's not an optimization. That's a fundamentally different method of solving problems. It turns out that when you approach problems this way, efficiency and trust come from the same source. Hallucinations aren't random errors. They're the inevitable result of complex search patterns that have no ability to check themselves against a single overarching logic. The system explores 1,000 branches, picks the most statistically likely output, and presents it with confidence. But nothing in that process ever asked whether the answer is structurally sound. Mode T can't hallucinate because it doesn't generate output from insufficient information. If the problem can be solved, it solves. If it can't, it stops. 8.6 times. Same answer. A fraction of the work. And notice the pattern. As the problems get harder, the gap widens. The architecture eliminates more work when there's more work to eliminate. Now we leave the protocol layer entirely. Everything you've seen so far relied on the model self-reporting its effort. Reasonable people can question that. So this tab uses programmatic solvers. No AI model is involved. Every operation is counted by the code itself. The results are deterministic and reproducible. I want to be clear about what you're about to see. This is not a heuristic. A heuristic finds approximate answers. Good enough, close enough, within some margin. This is an exact solver. It finds the provably optimal solution. The same optimal solution as brute force. Zero quality loss. What changes is how much work it takes to get there. The method is patent pending. If you're a computer science engineer and your first instinct is skepticism, good. That's the correct response. What I'd ask is that you watch the numbers, check the methodology, and evaluate what this actually does rather than what you assume it can't. It doesn't solve P versus NP. It doesn't make hard problems easy. It removes work that was never going to contribute to the answer. And it compounds. The baseline is brute force. For 9 cities, it evaluates every possible permutation. That's 8 factorial, 40,320 routes. Every single one. No shortcuts, no heuristics, no early termination. It checks them all and keeps the shortest. That's the control. Mode T finds the same optimal route. Zero quality loss, verified against brute force. The difference is the work it takes to get there. The how is what's under patent. Then there's Fractal. Same architecture, but applied recursively. The gate has a gate, and that compounds. 9 cities, 40,000 permutations for the baseline. Mode T, about 400 operations, roughly 100 to 200 times more efficient. Same optimal route. Fractal, around 100 operations, 300 to 800 times more efficient. Same optimal route. Q equals 0. Verified. 10 cities. The baseline went from 40,000 to 362,000. 9 times more work for one additional city. Mode T went from 400 to about 700. The EMF didn't stay the same. It grew. Roughly 500 to 900 times. 11 cities. Baseline, 3.6 million permutations. Mode T, about 900. Fractal, about 190. The fractal EMF is now above 18,000. For one additional city, the baseline's work increased by 10 times. Mode T's barely moved. That's superlinear scaling. The harder the problem gets, the bigger the advantage. The gains don't flatten. They don't converge. They diverge. Every additional city makes brute force exponentially harder. The architecture's efficiency grows proportionally. The harder the problem, the more work it eliminates. 12 cities. The baseline would need to evaluate 39,916,800 permutations. We're not going to wait for that. Mode T and Fractal solve it in seconds. 13 cities. 479 million permutations for brute force. 14 cities. Over 6 billion. The architecture keeps going. The wall that brute force hits, this architecture walks through it. Not by approximating. The solutions are exact. Patent pending.